I'm going to be talking about sea surface temperature in Zarr. It's kind of a two-part series talking about the creating Zarr store for AWS public datasets and also using a really cool new library called Rechunker to optimize MUR SST queries for OceanHackweek solutions and performance. So to lead through a little bit of history into this project, so we published a sort of V0 Zarr store to AWS PDS in January 2020. And as I'll talk about in a little bit, we wanted to try out some different chunking strategies for that data set in July 2020. So it sort of had some challenges just trying to rechunk the data set that I'll talk about. In July 2020, a package called Rechunker was released by Ryan Abernathy, which was great timing because then we were able to use Rechunker to rechunk this Zarr store in time for OceanHackweek, which just happened. This is sort of from the original release. So I created some of these slides back in February to present on the original sea surface temperature Zarr data store. And just as a little bit of background, so I was introduced to Shel Gentiman, who's an oceanographer and a climate scientist, and we met at this NASA workshop on maximizing the return of scientific data. And we sort of developed a little bit of a relationship after that. And she said, hey, it would be amazing for the oceanographic community if this sea surface temperature data set were in Zarr for our analytics on the cloud and using all these great Pangea resources. And I said, sure, why not? What could be so hard when, really I didn't quite know what this would involve. So a little bit of background just on the data set, so if you're interested from the sort of science perspective. So this is a multi-scale, ultra-high resolution sea surface temperature data set. So it's a sort of fusion product from these different instruments, AMSR-E, MODIS, and the advanced very high resolution radiometer. And it includes data on sea surface temperature from 2002 to present. So it's a pretty good time, has a pretty good time extent as well. And it's produced by Kodak, which is a NASA DAC. So what is Zarr? So Zarr is a chunked, compressed, n-dimensional array storage format. This chunking and compression of source files enables optimized queries by accessing only the data you need. So users no longer have to download and read in large volumes of files, which include extra variables, temporal and spatial extents. So why Zarr? So this is sort of my slide on sort of saying, it's not just Zarr, it's the paradigm of basically enabling people to have access to analytics optimized data stores. So this is sort of how I summarize the problem. So in the past, we have been, downloading files to our local desktops. Right now, we're moving towards these cloud-hosted systems where all of the, all of the data is moving to the cloud. And then in the future, we're hoping that all of these data sets become basically accessible in a sort of zero download paradigm where data is directly queryable via these analytics optimized data stores. So there's some pros and cons of Zarr. So some pros, compress, optimized for querying, readable by the popular Python library Xarray, which can be used with Dask for distributed computing. Some cons, it may not include all data and metadata described in the archival format. A useful Zarr store requires anticipating how users will want to query and access the data. So, we're going to talk a little bit more about how the data itself was chunked in terms of time, latitude, and longitude, and how, certain different ways of defining your sort of chunk shape might be optimizing for different use cases versus like time series versus time series of a specific spatial extent versus sort of doing a global average, for example, at one point in time. Support is mainly in Python. Yep, so sort of one sort of weakness is support in these other languages, and no clear ownership or governance model. So that might be changing. So another good alternative is TileDB, which is actually in the parallel track here right now. Also, if anybody has burning questions, I am fine with interruptions. So if anything about this is unclear, feel free to sort of chime in or post questions, I guess, in the chat. So a way that I like to picture the problem that Zarr is solving is, like, let's say you want a time series of sea surface temperature for just like this small area of interest in the Atlantic. With the traditional file archive, you'd have to download 18 years worth of global data to read in just like this small bounding box. But let's say that you're using Zarr, then you can just grab that small piece and transfer that amount of data, you know, into the memory, basically, of your compute resources. So how did we do this? So like I said, the data, the original netcdf, how did we do this? This being, how did we generate the Zarr store in practice? So all of the netcdf files were, you know, not on the AWS cloud, but on the PODAC resources, which enabled PODAC data center, which enabled us access through HTTPS, OpenDAP, or WebDAV. So the fastest way to basically access this data was to mount that WebDAV server with this utility DAVFS onto an AWS EC2 instance. And then we were able to use AWS FSX, which is basically a way to create a sort of file system cache on top of AWS S3. So we can integrate that with S3 as sort of our output location, and mount the FSX instance with the EC2. And then we can run our toZarr operation, which is a sort of create the Zarr store and then append for 1 year and repeat for 18 years. So I used both the create an original Zarr store, and then I basically appended periodically a year of data and repeated that for 18 years. And so there's a lot of trial and error that went into this approach, but this is where we ended up. And then basically use this repository sync feature of AWS FSX to get the final Zarr store output to S3. The other step in this process was finding the right chunk size. So if you look at this top column, the top row here, this is basically a chunk shape that is time, latitude, and longitude. So sort of looked at some smaller chunk sizes for time originally, just based off of, you know, the fact that you originally get the files all in one file per day, right? So your original chunk shape is going to be of a time step of 1 if you just read in like netcdf files. So it sort of made sort of the default was to go with sort of a small size of the time chunk, which ended up sort of being the wrong approach, which I'll talk about in a little bit. But at first, you know, for this first iteration, we were looking at these smaller sizes of the time dimension. And for that, we ended up going with, you know, this sort of intermediary approach of 5 by 1800 latitude and 3600 longitude. And that, yeah, and so that's basically what we ended up choosing in terms of both performance and open. It was a good balance between the performance in these types of queries, right? So we looked at testing, calculating the global mean versus calculating an annual mean over different temporal and spatial extents, and then also balancing that with the time to actually open the store itself. Yeah, so this is, you know, sometimes it helps to see what things look like in practice. So what does the output Zarr store look like? So you have basically these directories, which are storing the dimensions and the coordinates, along with these .z files, which are storing like the actual Zarr metadata that's used by libraries to support reading in just the chunks of data that you need. And then you get these, the actual data itself is stored in these files that you can see on the left that have these names that identify their actual chunk location in the larger data store, right? So this is like, goes all the way from 0.00 to your final, the shape of your final chunk further in the bucket directory. And then we put it on AWS public datasets. And just to see what this looks like a little bit in practice in terms of, this is just to demonstrate what the Zarr generation code looks like. So this is the code to create and append the Zarr store. So we have to, generate a list of files, the netcdf files from PODAC, and then, set some constants where we're going to put the data. And then, we started with basically creating an initial Zarr store, but then, so that's basically if you're going to create the initial Zarr store, you just do that in a simple way, but not append. And then basically when you loop through each additional year, you're going to continue to use the Zarr append, that I'm losing where the actual append, append dimension. So here, basically, if we're not, so basically if you're not, the first day of this data set is 152 and the first year of this data set is 252. If you're gonna do that, you just basically, your argument of mode is right? You're creating the original Zarr store. Otherwise, you're going to basically append, you're going to switch your mode to append. So you're going to append to an existing store and then append on this time dimension. So that's basically how that works. And then we have some just code that is basically testing the, testing the data itself, right? So we want a sort of simple step to basically say, hey, let's make sure that the data that's stored in our Zarr store is the same, data or values that we get back from the netcdf files themselves. So yeah, that's basically creating the Zarr store itself. Using the Zarr, so Shell created some really great tutorials on how to use, how to use the Zarr store itself. And you can check those out in her repository and go more into detail there. But just to show what this looks like, so there's a couple of these in here. If you go into one of these directories, like called make Zarr, for example, you can go ahead and actually open up this. This is going to take a couple, it'll probably take about 30 seconds just to open this Zarr store. And then, so we'll let this run. But basically, after loading these libraries, we're basically going to just use a very simple FS spec library to open the public data sets, and it's public, so none of this is true. And then we can generate a time series. So yeah, so we get back the data variables, analyze SST, analysis error, mask, and CI's fraction. And then we are able to generate a time series for a given latitude and longitude over the 20 years in just 2.3 seconds in this case. So that's the little demo portion. So we use Dask for generating some of these things and running some more advanced queries. So I just really like this GIF. Sort of sometimes when you do exciting things with Dask, you get really cool, Jupyter Lab integrations like this, which I'm very grateful for because it gives you a little bit of a power trip to see all these computers working on your behalf to actually do this analysis. Okay, so with that, I'm going to talk about some challenges we ran into. So full disclosure about the thing that I just showed, that was using a new chunk shape. So that was our original chunk. It was not using, it was not using this chunk shape. This was our original chunk shape of time, 5, latitude, and longitude. And so for opening the data set for this chunk shape scheme, opening a data set took about 1 minute, which is not that bad, but generating that same time series took 33 minutes. So, so originally, you know, we didn't have that performance that I just demonstrated. Basically, you know, I sort of went with a sort of wrong approach based off of what we ultimately wanted. So I had some issues trying larger chunk shapes originally, or trying to rechunk originally. You know, this wasn't implemented originally with Xarray, the ability to go from a Zarr store with a time dimension, basically to upscale this time dimension into a larger chunk shape, was not implemented. There's a fixed workaround for this, but when I did go up to at least 60 time steps for that dimension, this didn't display much greater performance. Additionally, trying to rechunk with this existing Zarr, when I tried to increase to time chunks of things like 379 or 189, basically got a lot of, you know, sort of memory issues with Dask workers, kernel crashing. So a lot of memory constraints that I was sort of trying to handle here, or having sort of like a timeout connection between like the scheduler and the workers. So felt a little bit stunted at this point. However, then we got a new library, thanks to Ryan Abernathy again, called Rechunker. So what is Rechunker? So Rechunker is a new Python library called Rechunker, which performs efficient on-disk rechunking of a chunked array storage formats. So really simple code. Basically, you're going to give it the target chunks that you want. So what is the shape that you finally want? What is the maximum amount of memory that you have for your Dask workers to actually generate these new chunks? And then create a Rechunker plan, and then basically give it a temporary store, and then, you know, sort of execute the plan. So this is really great because Dask's rechunk function runs out of memory when trying to rechunk. Every source chunk goes into, for example, because when every source chunk goes into every target chunk, you can easily sort of run out of memory. So say in the case that this was pretty much our case, or very close to it, in the case that time chunks start at 1 step and we need to go into a target chunk of the full temporal extent. So this is what happens when you have time series, is when you have a time series that's produced as 1 file per day, and you're trying to create a time series that goes over, you know, 6,443 in our case. That's how many days are in this time set. You can quickly run out of memory trying to generate that. So how does Rechunker work? So you have your input chunked array and your output chunked array, and it writes intermediary chunks to a temporary store, respecting the memory limits of Dask workers. So the difference with Dask's rechunk is this reliance so Dask was, so with the new library, we're using a persistent store for temporary intermediary chunks that enables us to basically not overrun the memory limits of our Dask workers. So you can see this in a really great diagram that I did not create, so credit Ryan. So basically you have your source on the left-hand side, which has its shape, and then you can sort of create these smaller intermediary chunks as part of the plan, because this, you know, each of these intermediary chunks are basically representing how much memory you want to give to your Dask workers, or available on your Dask workers, and then you can sort of put those things together and write it to your target. So this is what the rechunking code looks like. There's a link to it here, but essentially I was able to take the original Zarr data store, which you can see in this load the MUR SST dataset from AWS PDS. You just load that up. And then you create your plan, right? So I have my temporary store here under the Rechunker plan. That's basically, I can use S3 as well for this, for my temporary store. Create my target chunks. I want a target chunk to optimize for this time series analysis. I'm going to use a target chunk of actually time being the full temporal extent for this data set. And then I'm just going to give a memory limit of 2 gigabytes. And then I'm going to create my plan, and then I'm going to execute it. And it's that easy. It was a little bit slower than expected. So estimated time to complete was 100 hours originally. And so the following slides sort of go into details about what was causing this to be slow. So, you know, thankfully there's a really active community around Pangeo and Pangeo data and Zarr. So when I open this ticket saying, hey, you know, this is what I'm trying to do, I'm a little concerned that it's going to take 100 hours. Seems like I must be doing something wrong. This thing on the right is basically, you know, it's not even the full length of that thread. So there's a lot of really interesting, great debugging that came from the community, troubleshooting this sort of performance issue, and highlighted some interesting things. So one of the things is basically highlighting that a good way of sort of troubleshooting this type of issue is just to see maybe how fast you can read and write a Zarr object, just, you know, operating directly on it without Dask distributed. So so I think a couple people were able to demonstrate that reading or writing of a key was pretty fast at just 15 seconds if you just call it directly. But if you run it, when you can analyze these things using Dask distributed, the dashboard interface, if you look at that, you can actually see that it's taking up to 70 seconds when the same read-write operation is happening in Dask distributed. So there's something going on inside Dask that's making a single read-write cycle take 10 to 80% longer. And that was one person's quote, and another person found that it was taking 500 to 1,000 times longer. So it appeared that this was a combination of issues. So first of all, the compression itself was happening in a thread, and they found that reading and writing Zarr arrays is slower when done in a thread when using a multi-threaded flash compressor. So these Dask workers are running in a thread, so they're suffering from this problem. Another thing was variable task duration. So this is more of a symptom than a diagnosis, but basically finding that, there's the task durations for Dask distributed is kind of going back to what I was saying earlier. Is there something going on in Dask distributed that's maybe making it take longer? So the task durations are going anywhere from 20 seconds, which is kind of what we would expect from our little test, to 200 seconds. And also finally, writing to S3 using S3FS. So essentially, the way that I was able to speed things up in terms of rechunking this Zarr store was just not using S3 for the temporary store, because this latency between, the Pangeo cluster that I was using and S3, writing to a temporary store for S3 was not totally necessary. I was able to basically use one large instance with a whole lot of local storage, basically 3.2 terabytes, which is the size of the whole store for temporary storage. So with using that for the temporary storage, just a local EBS volume, I was able to complete this rechunking in about 10 hours. Yeah. So rechunking was done with a big instance with big temporary storage. And so we went from, a time, this shape of 5, 1799, 3600 to time 644, 6443, latitude, longitude of 100. And that was great because it took us from, you know, time series going from about 3 minutes for a given latitude, longitude time series taking about 4 minutes to 2 seconds, you know, yeah, on the order of magnitude of 2 seconds. So it's like about 100 times faster. And then this new data store was used in OceanHackweek, which is an event put on by the eScience Institute at University of Washington and a bunch of other folks most recently. So they're using it to study marine heat waves, which basically the cool thing is that, you know, typically marine heat waves, it's been, they've only been able to study these marine heat wave phenomenon, you know, with a temporal extent of about 5 days. And using the Zarr store, they're starting to build out that model so that you can basically do sort of a grid search over different temporal and spatial variability to see how marine heat waves, you know, not just 5 days in length, but over different regions, over different time lengths, what those look like, and then eventually to correlate those marine heat wave phenomena with other types of phenomena, right? Like things in precipitation and biodiversity. So that's what that project is all about. Yeah, and then this is just my thank you slide. I had a lot of help working on both this data store as well as, you know, rechunking and input into the performance issues of doing rechunking. So I wanted to give a shout out to these folks. And with that, I will take any questions.
I had one question around when you showed the chunks in the S3 bucket.
Mm-hmm.
It seemed like they were like each chunk was stored as a separate file that was less than a megabyte. Is that the format where each chunk is like in a separate file?
So those were particularly small chunks. They should really be more like 100 megabytes, but that doesn't really answer your question, right? What was your question again?
No, that does sort of answer my question. And
yeah,
because yeah, it seems like that'd be like a lot of small files. I mean, one of the things.
Oh yeah, that shouldn't be the case. That was like those particular files were quite small, but like the average was like 68 megabytes.
And then so for each of those, let's say 60 megabyte chunks, is that like, can you read portions of that chunk in through like the byte range request, or is that you sort of read
I don't
a chunk
think,
at a time?
Not that I'm aware of. I think you're reading just that you would read in the chunks as is. I don't think you would read a part of those chunks.
Gotcha. Cool, thanks.
And then I also see a question from Brian. Architecturally, if I understand, I see Dask on a local cluster as a top-level requirement for on-site. Keep the requirements to Zarr Smart Code Run as minimal as practical. Okay, I think that's just a comment. Unless, Brian, you wanted to expand on that. Cool. Well, if there's nothing else, we can end early. I am hoping to create a stack catalog for this data set as well. I think the definition of stack for Zarr is still something that is in development, but yeah.
Great, thanks, Amy.
Great, thanks.